Nickel, a natural corrosion fighter. When combined with other metals, it enhances the corrosion resistance of all common alloy systems. International Nickel, the leading producer of this unique metal, has been a world leader for more than 50 years in solving the many problems caused by corrosive action. Inco's extensive program of research and development with nickel-containing and other materials has greatly advanced the science of proper selection of materials for structures, equipment, and products. The knowledge gleaned over many years at Inco's product research facilities in North America and Britain has played a major role in helping man to overcome the ever-present natural forces of deterioration. In nature, the forces that cause corrosion are as relentless as the surge of the sea. Corrosion turns structures and machines into crumbling skeletons, piles of junk. It turns gleaming buildings into useless shells. In the United States alone, it is estimated that corrosion costs over $10 billion a year. Different metals are affected to varying degrees, and corrosive attack takes many forms. Attack may be by general tarnishing or rusting, with occasional perforations in highly affected areas. The metal may suffer highly localized attack by pitting. Even hard, tough metals can crack as a result of corrosion. Deterioration may be confined to crevices, under gaskets, or in sockets. Corrosion can also have the effect of removing one of the constituents of an alloy, leaving a weak residue. It is the purpose of this film to explain how corrosion occurs and some of the things that can be done to stop it. The basic cause of corrosion is the instability of metals in their refined forms. Because of this free energy relationship, the metals tend to revert to their natural states through the processes of corrosion. In the case of iron, the action of rain forms rust. When you analyze rust, you find it is iron oxide. When you analyze natural iron ore, you find it too is iron oxide. In rusting, iron has simply reverted to its original native state. The basic nature of corrosion is almost always the same. A flow of electricity between certain areas of a metal surface through a solution capable of conducting an electric current. This electrochemical action causes destructive alteration, or eating away of metal at areas which are called anodes, where the electric current leaves the metal and enters the solution. We have the presence of an electrolyte as one of the first requirements of corrosion. An electrolyte is any liquid that contains ions. Ions are electrically charged atoms or groups of atoms in solution. Pure water, for example, contains positively charged hydrogen ions and negative in equal concentration. Our corrosive environment may be any form of moisture ranging from plain water to the strongest acid or the strongest alkali. It may be just moisture condensed from the air, or it may be salt water. But in any environment, regardless of its nature, the basic mechanism of corrosion is in principle the same as the electrochemical action in an electric dry cell such as we've all seen. There is always an electrolyte, an anode, and a cathode where current enters the metal from the electrolyte. These electrodes may consist of two different kinds of metal, or they may be different areas on the same piece of metal. In either case, there must be a potential difference between the two electrodes or areas so that electricity will flow between them. A wire or other metallic path is necessary to complete the circuit for the flow of electrons, which are negatively charged particles moving in the wire from the negative to the positive electrode. The popular concept of current flow, as used in this discussion, visualizes imaginary positive charges moving in the opposite direction. This electron path may be provided by any kind of conductor or merely by the fact that metals are in contact with each other. let us consider what takes place at the anode when corrosion occurs. Remember that the anode area is that point, by our popular concept, that the current enters the solution. Several things happen simultaneously at this location. Positively charged atoms of metal detach themselves from the solid surface and enter into solution, while the corresponding negative charges in the form of electrons are left behind in the metal. The detached positive ions bear one or more positive charges. Each iron ion carries two charges and releases the electrons which travel through the metal to the cathode area. What has been taking place at the cathode all this time? As you can see, the electrons reaching the surface of the cathode through the metal have been meeting and neutralizing some positively charged hydrogen ions which have arrived at the same surface through the electrolyte. In losing their charge, the positive ions become neutral atoms again and may combine to form molecules of hydrogen gas. The reduction of hydrogen ions results in the accumulation of a relatively high concentration of OH ions, which are left behind to increase the alkalinity at the cathode or make the solution less acid here. The formation of hydrogen in this type of anode-cathode corrosion cell can be shown by placing a piece of ordinary iron in a solution of hydrochloric acid. A vigorous formation of hydrogen bubbles is seen. Under such conditions, the metal corrodes very quickly. The usual dissolution of the metal is occurring only at the anodes, with hydrogen bubbles forming only at the cathodes, even though it may appear that they are being released all over the surface rather than at well-defined cathodic areas. The anodic and cathodic areas shift from time to time. This permits substantially uniform corrosion to occur. If we could see this action through a powerful microscope, we would see many tiny anode and cathode areas on the surface of the metal. These areas are often extremely small and so numerous as to be almost inseparable. There are many causes for this, such as inclusions in the metal, lack of homogeneity, surface imperfections, orientation of grains, localized stresses, and also variations in environment. If we could see just one anode and one cathode in a giant view, we would see electrons released by the formation of each ferrous ion flowing through the metal from the anode to the cathode, where they meet the hydrogen ions in solution, which act as electron acceptors at the cathode surface. One electron is accepted in the discharge of one hydrogen ion. The hydrogen then appears as hydrogen gas coating the metal surface. As this process continues, oxidation and corrosion of iron occurs at the anodes, and plating out of hydrogen occurs at the cathodes. This formation of hydrogen molecules and the evolution of hydrogen gas are the principal reactions in corrosion by acids. Reactions involving oxygen dissolved in the electrolyte can also occur to complete the cathodic reaction. Oxygen can react with the accumulated hydrogen to form water, and by removing it, may permit corrosion to proceed. In doing this, oxygen acts as a cathodic depolarizer. As such, in neutral solutions where the hydrogen ion content is quite low, the concentration of dissolved oxygen and/or its availability are usually the rate-controlling factors in the corrosion reaction. The products of the anode and cathode processes frequently meet and enter into further reactions that yield many of our common visible corrosion products. For example, with the corrosion of iron and water, the hydroxyl ions from the cathodic reaction, in their migration through the electrolyte toward the anode, encounter ferrous ions moving in the opposite direction. These ions combine to form ferrous hydroxide. This soon becomes oxidized by oxygen in solution to form ferric hydroxide, which precipitates as a form of iron rust, with which we are all too familiar. Depending on the alkalinity, oxygen content, and agitation of the solution, this rust may form either away from the iron surface or right next to it, where it can exert more of an influence on the further progress of corrosion. The action of oxygen in furthering corrosion can also be demonstrated by placing iron turnings in two flasks filled with water. We'll allow oxygen to bubble through the water in one flask to supply it with oxygen, and we'll saturate the second flask with nitrogen, which drives oxygen out of solution. After they bubble for 2 or 3 hours, we'll find that the iron in the oxygen-free nitrogen solution is as bright as ever. But the iron in the water saturated with oxygen has already begun to rust. One of the causes of corrosion is differences in the electrical potential of dissimilar metals coupled together and immersed in an electrolyte. The resulting attack on one of the metals is known as galvanic corrosion. When we consider galvanic corrosion, it is essential to know which metal in the couple will suffer the accelerated corrosion. This is indicated in a rough way by the positions of metals in the standard electromotive series. Hydrogen is used as an arbitrary reference element. As we move up the list from hydrogen, one after another, the metals become increasingly reactive. Similarly, as we go down from hydrogen, the metals become increasingly inert. For example, if we put a piece of potassium in water, we get a violent reaction. Whereas, we can place a piece of platinum in strong nitric acid with no evidence of attack. The electromotive series also shows which metals can displace other metals in solution and suffer corrosion in the process. Any metal may displace one below it in this series. For example, iron can displace copper from solution with the copper ions acting as the acceptors for electrons in the corrosion of the iron. The displaced copper appears as a coating on the corroded iron surface. Similarly, hydrogen ions can act as electron acceptors for any metal above hydrogen in the electromotive series, as in the case of zinc in hydrochloric acid. Metals below hydrogen in the series do not readily displace hydrogen from solution and therefore are more resistant to corrosion, as in the case of copper dipped into the same hydrochloric acid as the zinc. Copper can displace silver from solution with the silver ions here acting as the electron acceptors in the corrosion of the copper. This electromotive series holds only for metals in particular concentrations of their own salts. In other electrolytes, the performance may be different. In studying galvanic corrosion, we use instead of the electromotive series a somewhat similar galvanic series based on experience with combinations of metals in seawater. Similar galvanic series can be developed for other environments. In any couple, the metal near the top of this series will be the anode and suffer the accelerated corrosion in a galvanic couple, while the one nearer the bottom will be the cathode and receive some galvanic protection. This means that any given metal may be an anode or a cathode, depending on the other metal with which it is coupled and their galvanic relationship in the environment encountered. Now the question is, what determines the speed at which galvanic corrosion will proceed? One factor is the relative difference in electric potential between the two metals. To illustrate, zinc coupled with aluminum in sodium chloride solution will generate a potential of about 300 millivolts, whereas with zinc and copper in the same solution, the potential is over 700 millivolts. The greater the potential difference, the greater will be the driving force behind the galvanic corrosion. As the galvanic corrosion reaction proceeds, the initial potential or driving force diminishes, and the potential of the anode drifts toward that of the cathode, and that of the cathode drifts toward that of the anode. This change in potential is called polarization. That at the anode, anodic polarization, and that at the cathode, cathodic polarization. In certain corrosion reactions, The polarization that occurs at the cathodes exerts more of a controlling influence than the lesser degree of polarization at the anodes. Consequently, in these cases, what happens at the cathode has greater practical importance. However, these cathodic reactions do not proceed with equal facility on all metal surfaces. As a result, some metals polarize more readily than others. It is necessary to know something about polarization characteristics as well as initial potentials before one can predict the extent of galvanic corrosion with any particular couple of metals. A direct example of this effect on galvanic corrosion is provided by an experiment in which pieces of steel of the same size are connected in an aerated salt solution to pieces of copper of different sizes, one large and one small. Both couples generate current, but notice, the couple with the large cathode produces the higher current. Thus we can see that it is hazardous to connect a small anode to a larger cathode. The following experiment further emphasizes this point. Here at Inco's Francis L. Lacouille Corrosion Laboratory at Wrightsville Beach, North Carolina, one of the world's leading facilities for studying corrosion in marine environments, we are taking from test in seawater riveted plates that have been immersed for several months. One of these plates consists of two pieces of steel joined by copper rivets. As we uncover the copper rivets, we see that they are in good condition and that there is no significant acceleration of the corrosion of the steel in their immediate vicinity. Now let us see what has happened to the steel rivets used to join the two copper plates. Here the steel rivets have been attacked very severely. The metals are the same in each case, but the unfavorable area relationship of the large copper cathodes and the small steel anodes was responsible for the severe galvanic corrosion of the steel rivets. The same type of cell that develops between two different metals may also develop on a single metal surface. Differences in potential from point to point can be created by differences in environment. Oxygen concentration cells can be set up to cause cathodes to develop at the areas of high oxygen concentration, and anodes where corrosion occurs at the areas of low oxygen concentration. The fact that electricity does flow between points where oxygen concentrations differ may be demonstrated with similar pieces of steel in each side of a two-compartment cell containing a dilute sodium chloride solution. No current flows when they are coupled through a microammeter. But if we bubble nitrogen through one side of the cell to reduce the oxygen concentration and oxygen through the other side to increase the oxygen content, we find electricity flowing with the steel and the electrolyte starved of oxygen acting as the anode, thus proving the existence of a corrosion current. Similar corrosion currents can be generated by differences in metal ion concentrations. The existence and location of anodes and cathodes in an oxygen concentration corrosion cell on a steel surface can be demonstrated by the changes in color of certain reagents as well as by the use of electrical instruments as in the preceding experiment. We have shown that the cathode reaction produces an increase in the concentration of hydroxyl ions as a result of removal of hydrogen ions or the reduction of oxygen. Phenolphthalein is a well-known indicator which develops a red color when the concentration of hydroxyl ions is increased to the point where the solution becomes alkaline. Therefore, if phenolphthalein turns red as corrosion proceeds, it will detect the existence of a cathode and reveal where it is. Similarly, potassium ferrocyanide is a reagent which produces a blue color by reaction with ferrous ions formed at anodic areas when iron corrodes. The appearance of this blue color, therefore, demonstrates the existence and location of anodes on iron. Using these reagents, we can show the development and location of the anode and cathode in a cell established on an iron surface within a drop of gelatin containing these indicators. Oxygen from the air is more accessible to the periphery of the drop and sets up a cathode there as shown by pink color. Simultaneously, an anode, shown by the blue color, develops near the center of the drop, which is less accessible to oxygen. Most frequently, the conditions that give rise to oxygen concentration cell attack are associated with the presence of a deposit at one point on an otherwise freely exposed surface. The metal outside the deposit will be readily accessible to oxygen, while that under the deposit will be shielded from it. This will set up a corrosion cell with the formation of metal ions in the anodic region under the deposit. Electrons will flow through the metal to the surface outside the deposit, and a cathodic reaction there will result in the reduction of oxygen to form hydroxyl ions. For example, this piece of metal with a little pile of sand has been immersed in salt water for about 2 months. As we drain off the water and brush aside the pile of sand, we find that accelerated attack has occurred under it. The color-changing reagents used previously to demonstrate oxygen concentration cells can be used as well to show the existence and location of anodes and cathodes in other types of corrosion cells, such as those set up between dissimilar metals or from point to point on a single metal surface. For example, let us take an iron nail with copper plated on the pointed half of it. We will place this specimen in a gel containing sodium chloride, phenolphthalein, and potassium ferrocyanide. As time passes, we will notice the development of a pink area around the copper-plated portion and a blue area around the bare iron half. By speeding up the action, we see that the colors become more intense with time, showing that iron continues to corrode and at the same time there is an increasing concentration. If we combine iron with a more active metal like zinc, we have a couple where now the iron acts as a cathode and the zinc as anode. Here we have an iron nail with the pointed end plated with zinc. We see now that the red color identifying the cathode develops at the iron half, where no iron goes into solution, and therefore no blue color develops. The zinc is corroding as an anode at the point and is consumed in providing protection to the iron. Since zinc ions do not develop a blue color with the ferrocyanide, there is no blue indication of an anode in this case. A similar technique may be used to show a local action cell on a single metal surface by placing an ordinary iron nail in a prepared gel. After several minutes, a pink area develops around the shank of the nail, indicating formation of a cathode. Blue areas develop around the cold-worked head and point of the nail, where the iron goes into solution, indicating that these areas are the anodes. So we have shown again that corrosion on a single metal surface is electrochemical and is caused by a flow of current between anodic and cathodic area. Stop-motion photography again reduces the time required for this action. As we observed previously with the zinc-plated nail, the iron was made to act only as a cathode, and its anodic action was suppressed by the flow of current to it from the zinc. This is a simple example of cathodic protection, which can be illustrated further by similar experiments. In the first case, we used zinc joined electrically to an iron nail as the source of the protective current, which makes the iron act as a cathode all over, as evidenced by the development of the red color, showing the presence of the cathodically formed alkali. Note the absence of any blue color on the specimen receiving current from the zinc. Final development of this color requires several hours, but we can follow it by stop-motion photography. Likewise, cathodic protection can eliminate destructive galvanic action as between the steel and copper in a partially copper-plated nail. Here we see that both the steel and copper are made cathodic, and no anodic corrosion of the iron occurs in the composite specimen which receives current from the zinc. This can again be followed by stop-action photography. This technique, called cathodic protection, is a common method of corrosion control. In practice, the protective current may be impressed from a generator rectifier or other external source through an appropriate inert anode, or it may be generated by the corrosion of metals such as magnesium, zinc, or aluminum. The phenomenon of stress corrosion cracking is one of the most serious materials problems faced by industry. It is perhaps best described as the brittle failure of a normally ductile alloy at tensile stresses well below the ultimate strength of the metal in a specific environment. For example, the common copper-zinc brass alloys can crack if small quantities of ammonia are introduced into the environment. Other examples of this destructive mode are the cracking of austenitic stainless steels in chloride-containing environments and of carbon steels in nitrate, cyanide, and strong caustic solutions. Alloy steels with yield strengths greater than about 175,000 pounds per square inch require only the presence of water and a tensile stress to fail through a type of stress corrosion cracking known as hydrogen embrittlement. If hydrogen sulfide is introduced into the aqueous environment, the maximum allowable strength level of such steels must be halved before danger of stress corrosion cracking no longer exists. A complete listing would include practically every alloy system. In addition to the specific iron requirement, other environmental factors affect the susceptibility of metals to stress corrosion cracking. Variations in temperature, oxygen content, stress level, pH, and metal structure and composition are all interrelated in determining overall sensitivity. Although a full theoretical explanation of stress corrosion cracking does not exist, a number of techniques can be used to reduce or eliminate failures. The most common practice is to substitute a resistant alloy not affected by the specific environment for the susceptible material. Other effective measures have been cathodic protection and the use of inhibitors. Sometimes the environment can be altered to remove the specific ion or control it at low levels. Limiting oxygen content has been effective. Shot peening has been used to introduce surface compressive stresses which offset residual and applied tensile stresses. The effect of oxygen on corrosion is variable and complex. We can see that it increases corrosion by acting as an electron acceptor and removing the film of hydrogen at a cathode. In higher concentrations, oxygen can also retard corrosion. Oxygen or oxidizing agents such as nitric acid can form invisible protective films of their own and in this manner reduce corrosive action. The metal is said to have been rendered passive. When some active metals become passive, they take on many features of the noble metals. For instance, iron made passive by an oxygen layer or oxide film approaches the noble potential of platinum and resists corrosion. This fact is easily demonstrated. Iron is active in hydrochloric acid. When we couple it galvanically to platinum and then measure the potential difference in hydrochloric acid, we find this potential to be about 700 millivolts. But if concentrated nitric acid, in which iron becomes passive, is substituted for hydrochloric acid, we find that the potential difference between iron and platinum has decreased to about 300 millivolts. However, the frail film responsible for the passivity of iron in this case is easily damaged. For illustration, active iron when dipped in a copper sulfate solution will cause plating out of the copper. But now, if we make a piece of iron passive by immersing it in nitric acid, a protective film formed by the nitric acid prevents corrosive action. If we dip this passivated iron into copper sulfate, no plating out of copper occurs, but a light tap is sufficient to rupture the passive film. The iron becomes active again. In slow motion, we can see that copper plates out radially from the point where the film is broken. An active area at the point of impact becomes anodic to the surrounding passive area acting as a cathode. The reducing action at the cathode destroys passivity and corrosive action spreads. This type of unstable passive film is obviously not a dependable means of protecting iron against corrosion. By alloying iron with chromium or a combination of chromium and nickel, the alloys develop a much more stable passivity, such as we have in stainless steels. Whether these iron-chromium and iron-chromium nickel alloys are active or passive depends on their composition and the environment. Iron with 3% of chromium is active in copper sulfate solution and plates out copper. With 6% chromium, the plating out is proceeding more slowly, but the alloy is still active. When the alloy contains about 12% or more of chromium, it achieves substantial passivity and will resist corrosion in many environments. And of course, the 18% chromium, 8% nickel stainless steel is also passive in copper sulfate. The increased chromium content and the presence of nickel have greatly extended the number of environments where useful passivity exists. This type of alloy is also much more easily fabricated and welded than the non-nickel stainless steels. This passivity is substantial and cannot be destroyed by striking the specimen with a glass rod, such as occurred with the ordinary steel specimen treated in this way. And just as happens with iron, the change from activity to passivity also changes the potential of stainless steel. When activated in certain environments, 18-8 stainless steel acts like iron and has about the same potential. For proof, here is a piece of 18-8 stainless steel and a piece of carbon steel immersed in warm sulfuric acid and joined through a millivolt meter to measure their difference in potential. At the start, the stainless steel is passive and shows a potential of 700 millivolts, more noble than the carbon steel. We now bring the carbon steel into direct contact with the stainless steel, so that hydrogen now forms on the stainless steel surface and destroys the film responsible for its passivity and its noble potential. When we take the piece of carbon steel away, we find that the potential difference between the stainless steel and carbon steel has fallen towards zero. Now let us introduce a piece of stainless steel that is still passive. We see that the potential difference between this passive steel and the activated stainless steel is as great as just observed between ordinary steel and the passive stainless steel. We can restore the passivity of the activated stainless steel by introducing nitric acid, which has a strong passivating effect. We see that the evolution of hydrogen on the activated stainless steel stops, and the potential drops towards zero. If we then substitute a piece of platinum for the stainless steel that was always passive, we now observe a small difference in potential. This shows that the once active stainless steel has regained its passivity and its noble potential. A difference in potential will occur when active and passive areas develop on the same piece of stainless steel. For example, the passivity of stainless steel depends upon a protective film of oxide, which while not visible is nevertheless very real. However, the amount of oxygen in the environment affects the stability of this film. The stability is also greatly reduced in the presence of chloride ions and high concentrations of hydrogen ions. Thus, should the supply of oxygen at any point on the metal surface be insufficient to maintain passivity in a chloride-containing environment, as a result of local shielding, a small local active area would develop, creating a large potential difference between it and the surrounding passive area. The result would be galvanic action between the small active area as anode and the large surrounding passive area as cathode, with intense corrosive action at the small active area. The development of these so-called active-passive cells causes corrosion in crevices where passivity has been destroyed. We can demonstrate the damage that results from the breaking down of a protective film and the creation of active-passive cells. For example, let us observe the effect of a rubber band around a piece of stainless steel, which is immersed in a dilute solution of sodium chloride and ferric chloride. By taking photographs after a period of time, we can see the rubber band cutting into the edge of the stainless steel. Oxygen cannot easily penetrate beneath the rubber band. Oxygen starvation causes the passivity to break down, creating an active area or anode beneath the rubber band, while the remainder of the surface being freely exposed to the dissolved oxygen acts as a cathode. Obviously, with passive alloys, it is necessary in some environments to avoid deposits or crevices which can exclude oxygen. Rust is a product of destructive action, but it may also have a protective value, although the mechanism of that protection is different from that of the passive films on stainless steel. Steels that show poor resistance to corrosion form heavy voluminous rusts that offer little resistance to the penetration of moisture, as in the case of this specimen exposed only 2 years at the Inco corrosion testing facility at Curie Beach, North Carolina. Differences in the rate of progress of corrosion are illustrated by the behavior of 3 steels. The one at the left is a steel of exceptionally low copper content. The one in the middle is an ordinary steel. And the one at the right is a nickel copper chromium steel. Notice the progress of rusting of these 3 steels during their exposure at Curie Beach for 3 years. The differences are due primarily to differences in the protective qualities of their rusts as a result of the addition of alloying elements. As shown by the weight loss versus time curves of these 3 steels, they all corrode at about the same rate at the start. But as the more protective rust develops on the nickel-copper-chromium steel, its rate of weight loss diminishes considerably, while the rate remains practically constant on the ordinary steel and actually increases a little on the steel of low copper content. Other alloys, of course, are even better than the low alloy steels in resisting atmospheric corrosion. and after many years continue to reflect the blue of the sky. For example, here are some panels of 18-8 chromium nickel stainless steel that have been exposed for over 10 years. Notice also how the Monel nickel-copper alloy racks, also in use for more than 10 years, have developed only a uniform superficial tarnish. And here is complete resistance to corrosion, provided by the complex nickel-chromium molybdenum alloy known as Hastelloy C. This specimen continues to serve as a mirror after more than 30 years' exposure at the atmospheric testing site of Inco's North Carolina laboratory. It has never been cleaned or repolished. The more we study corrosion, the more we realize two important facts. First, that corrosion is a natural process that can occur whenever there exists in an electrolyte a difference in the electrical potential of dissimilar metals, or a potential difference between separate points on a single metal surface. The rate of attack will be determined by the composition of the environment and other factors such as polarization, velocity, and temperature. Second, that corrosion can be controlled and avoided when we understand the conditions that cause corrosion currents to flow. When we understand these conditions, we know what action to take. We can, for example, choose the right materials for a given environment. Sometimes this choice is obvious, or it may require the advice of an expert, as in a large chemical plant using different alloys selected for particular purposes. Here, in a factory where watches are made, the humidity of the atmosphere is controlled in order to prevent corrosion of delicate mechanisms. We can apply an electric current to counteract the natural corrosion currents, a remedy called cathodic protection. We can give the metal a protective coating of paint, ceramic, or some more corrosion-resistant metal. We can develop new alloys to meet a given situation, or we can design and construct equipment free from built-in opportunities for corrosion currents to flow. What we understand, we can often control. And when we control corrosion, we are helping to save hundreds of millions of dollars every year. More important, we are helping to conserve our natural resources by making metals last longer.